3, 2, 1.
MDS to,
We have ignition. We have a liftoff.
Researchers picked up what they are saying possible signs of life beyond Earth in the form of mysterious electromagnetic signals.
After nearly 5 decades of remarkable space exploration, NASA's Voyager probe faced a critical malfunction, jeopardizing its cosmic navigation. A team of brilliant scientists and engineers was assembled by NASA to perform a precise system update and set Voyager 1 on its course. Now, something weird just happened after the completion of the system update that has scared scientists across the world. What shocking revelation did NASA discover in the system's previously stored data? Could this be evidence of extraterrestrials? Let's find out what happened after Voyager 1 received a software update 15 billion miles away in space. Picture the farthest man-made spaceship from Earth experiencing a malfunction without any existing playbook for resolving the issue. This was precisely the situation faced by NASA, prompting them to devise a brilliant plan. NASA then released a job posting for software engineers with a specific skill set. These programmers had to be an expert in Fortran and assembly, 2 programming languages from the 1940s and 1950s that are unfamiliar to most recent graduates. NASA formed a team of scientists tasked with the complete overhaul of Voyager 1's system, all the way from its location 15 billion miles away. Over several weeks, the team conducted extensive research and reprogramming, taking into account the unique modifications that had been made to Voyager 1 since its launch in the 1970s. Upon completing the update, NASA scientists made an astonishing discovery, an unexplored set of data that the probe hadn't sent in years. Something weird just happened after Voyager 1 received a software update 15 billion miles away. But to understand exactly how this could happen, we need to understand some context. In the 1960s, an exceptional proposal surfaced, a daring initiative to undertake a grand expedition across multiple planets, venturing into the mysterious realms of the outer planets located in the vast expanse of our solar system. This audacious venture, aptly named the Grand Tour, sought to dispatch unmanned probes to explore Jupiter, Saturn, Uranus, Neptune, and even Pluto. What made this plan truly remarkable was the fortuitous alignment of these planets, an uncommon occurrence that would grace the cosmos in the late 1970s and not repeat itself for a span of 176 years. Taking advantage of this celestial alignment, the twin Voyager spacecraft, Voyager 1 and Voyager 2, were triumphantly launched in 1977. The aim was to leverage the gravitational force of Jupiter as a slingshot, propelling them on an extended trajectory to the outermost realms of our solar system. Initially, the primary objective of these spacecraft was to unravel the mysteries of Jupiter and Saturn. However, their astonishing discoveries compelled the extension of their mission parameters. With newfound resolve, Voyager 2 embarked on a groundbreaking voyage, venturing further into space to investigate Uranus and Neptune, an unprecedented feat that remains unmatched by any other spacecraft to this day. Innovative remote control programming endowed the Voyager probes with enhanced capabilities, surpassing their original potential when they embarked from our home planet. Over time, Voyager 1 and Voyager 2 orchestrated a magnificent odyssey, encompassing the exploration of all the major outer planets of our solar system, meticulously examining 48 of their captivating moons, and unraveling the intricate systems of rings and magnetic fields that these celestial giants possess. In December 1977, Voyager 2 ventured into the asteroid belt, with Voyager 1 traversing at a swifter pace, overtaking its companion a mere 9 days later. February 1998 marked a monumental milestone for Voyager 1 as it surpassed Pioneer 10, becoming the most distant human-made object in the vast expanse of outer space. In 2002, Voyager 1 took its leave from the solar system, ascending above the ecliptic plane at a striking angle of 35 degrees, propelled forward at an astonishing velocity of 39,000 miles per hour. Voyager 2, on the other hand, charted a divergent path, descending below the ecliptic plane, venturing forth at a remarkable angle of 48 degrees and an impressive speed of 30,450 miles per hour. Voyager 2 claims the record reaches more planets than any other creation of a man-made probe. Meanwhile, Voyager 1 proudly reigns as the bravest traveler from Earth, venturing further from its place of origin than any other explorer. Remarkably, both Voyager 1 and Voyager 2 concluded their exploration of the outer planets within the initial 12 years of their momentous mission. Having fulfilled their primary objectives by 1989, these intrepid Voyagers stood poised to embark on a new chapter, exploring realms beyond the confines of our solar system. In January 1990, with their sights set on destinations far beyond the solar system, the project's designation was fittingly altered to the Voyager interstellar mission. Thus, these indomitable travelers persist, venturing into uncharted territories where no earthly creation has ever soared. Voyager 1 is no ordinary spacecraft. It is an extraordinary testament to the ingenuity of NASA's brilliant engineers, defying the relentless passage of time. Crafted with unrivaled precision, this interstellar pioneer boasts a remarkable array of features that have facilitated its journey through the cosmos for almost 5 decades. Among its many notable attributes is its robust radio communication system, meticulously designed to operate even beyond the celestial boundaries of our solar system. At its core lies a colossal 3.7-meter high-gain CAG grain antenna, serving as the vital conduit for transmitting and receiving radio waves, bridging the vast expanse between Voyager 1 and our home planet through the Deep Space Network stations. When direct communication becomes unfeasible, Voyager 1 relies upon its dependable digital tape recorder, DTR, capable of storing approximately 67 megabytes of data for subsequent transmission. To put this feat into perspective, signals from Voyager 1, as of 2023, endure a staggering 22-hour journey through the depths of space to reach Earth, an awe-inspiring testament to the vastness of the cosmos. Equipped with sophisticated cameras, Voyager 1 possesses the ability to capture celestial wonders, immortalizing distant planets, their captivating moons, and realms beyond. Fascinatingly, these visible light cameras operate under the guidance of an imaging parameter table, meticulously stored within one of the spacecraft's digital computers. While Voyager 1's camera system depends on predetermined instructions, it is worth noting that more contemporary space probes, developed from the 1990s onwards, have embraced fully autonomous camera systems. Steering away from the traditional, Voyager 1 relies on its ingenious computer command system, CCS, to orchestrate its operations, a marvel of 1970s technology that controls various spacecraft functions, encompassing command decoding, fault detection routines, antenna pointing routines, and spacecraft sequencing routines. An upgraded version of the CCS initially employed in the 1970s Viking orbiters, it stands as a testament to the enduring power of robust engineering. Before we discuss what just happened after Voyager 1 received a software update, you would want to find out what's behind the longevity of Voyager 1. What accounted for the success of the Voyager probes? As you would expect, Voyager 1 and Voyager 2 spacecraft were equipped with an impressive array of specialized scientific instruments, comprising intricate suites and subsystems, which accounts for the longevity of the probes. These remarkable instruments are primarily situated on the spacecraft's body, resulting in a staggering total of 65,000 individual parts for each probe. While the passage of time has taken its toll, only a handful of instruments continue to function aboard these intrepid explorers. One of the enduring instruments that remain operational on both Voyager 1 and Voyager 2 is the low-energy charged particle detector. This remarkable device, equipped with 3 sets of particle sensors, tirelessly measures the influx of low-energy particles and determines their velocity. By diligently scrutinizing cosmic radiation and particles emanating from the Sun, planets, and interstellar space, this detector provides invaluable insights into the composition and behavior of these cosmic entities. Venturing further into the realms of cosmic inquiry, both Voyager probes are equipped with a cosmic ray instrument. This instrument, with its remarkable capability to detect highly energetic particles originating from the Sun and other galactic sources, currently serves a pivotal role. It gauges the abundance of particles within the protective bubble of our sun's influence, as well as those originating from interstellar space. These readings serve as critical markers for scientists, aiding them in pinpointing the precise moment when Voyager 1 ventured into the vast expanse of interstellar space. Another noteworthy instrument that continues to operate on both Voyager 1 and Voyager 2 is the plasma wave subsystem. Utilizing its two elongated antennas, which extend at right angles to one another, this subsystem diligently measures the electrical field components of potential waves encountered during the probe's journeys. Originally intended to study these phenomena on the outer planets, the instrument has now assumed the role of unraveling the mysteries of plasma waves as they permeate interstellar space. Its active involvement in both spacecraft ensures a wealth of data for scientists to analyze and comprehend. The magnetometer, originally tasked with investigating the magnetic fields of the outer planets, has now transitioned into a new realm of scientific inquiry. Its primary objective is to probe the transition region between the interplanetary and interstellar media. By examining the magnetic characteristics at the boundary where the sun's magnetic influence gives way to the magnetic field of interstellar space, this instrument sheds light on the intricate interplay between these cosmic forces. In addition to these stalwart instruments, Voyager 1 and Voyager 2 continue to rely on the plasma science instrument for crucial data acquisition. This instrument tirelessly seeks out the lowest energy particles within plasma, while also possessing the capability to discern particles moving at specific velocities. Furthermore, to a limited extent, it can ascertain the direction from which these particles originate. As the spacecraft embarks on its interstellar sojourn, the insights provided by this instrument become increasingly vital. While some instruments have succumbed to the ravages of time or have been intentionally deactivated to conserve power, the diligent efforts of the Voyager team persist. Non-essential instruments were permanently shut down in 1998, 21 years after the initial launch, in a bid to preserve resources. Additionally, NASA has systematically deactivated heaters on both spacecraft as part of their power-saving strategy. The power source for each Voyager craft resides in a group of 3 radioisotope thermoelectric generators, RTGs. These remarkable devices derive their power from the decay of radioactive plutonium-238, transforming heat energy into electricity. However, as the plutonium-238 continues to decay, a time will come when it can no longer sustain the instrument's power requirements, resulting in the cessation of all scientific operations. While this inevitable power decline is projected to occur around 2025, the Voyager team endeavors to extend the lifespan of both spacecraft until 2027. This date holds special significance as it marks the 50th anniversary of their momentous launch. To ensure continuous communication with Earth, each Voyager probe is equipped with a pair of thrusters. These thrusters, though not intended for propulsion, play a crucial role in reorienting the spacecraft, ensuring that their antennas consistently point toward our home planet. By emitting brief but precise pulses or puffs, lasting mere milliseconds, these thrusters delicately adjust the spacecraft's position, enabling vital communication to be maintained. What recent malfunction has caught the attention of scientists, and why did NASA decide on a software update? In recent times, the iconic Voyager 1 spacecraft has encountered a series of troubling challenges that threaten its very existence. One of the pressing concerns that has arisen is the occurrence of garbled or corrupted telemetry data. As Voyager 1 traverses vast distances, it relies on transmitting crucial information back to Earth to keep scientists informed of its progress. However, on several occasions, the transmitted data has arrived in a distorted and unintelligible form, leaving scientists grappling with the daunting task of deciphering its true meaning. This phenomenon has posed a significant hurdle in comprehending the spacecraft's current state and the environment it encounters on its interstellar voyage. Compounding these communication challenges are the signs of aging and deterioration that have manifested within Voyager 1's thrusters. These vital engines, responsible for reorienting the spacecraft and ensuring its antenna remains pointed towards Earth, have begun to exhibit signs of wear and malfunction. As the thrusters falter, the delicate balance required to maintain constant communication with our planet becomes increasingly precarious. The risk of losing the ability to receive crucial data from Voyager 1 looms ominously, potentially severing our connection with this awe-inspiring emissary of exploration. The implications of these problems extend beyond mere technical difficulties. They have the potential to spell the demise of Voyager 1, a spacecraft that has defied expectations and exceeded its intended lifespan. Without the ability to transmit clear telemetry data and without reliable thrusters to maintain its orientation, the fate of this trailblazing probe hangs in the balance. The loss of Voyager 1 would not only signify the end of an era, but also rob us of invaluable insights into the mysteries of interstellar space. In the face of these challenges, NASA embarked on an impassioned mission to overcome obstacles and extend the lifespan of Voyager 1. They meticulously analyzed the garbled telemetry data, employing sophisticated algorithms and innovative techniques to extract meaningful information from the jumbled signals. Simultaneously, they explored alternative methods to compensate for the failing thrusters, delving into the possibility of utilizing other onboard systems or devising ingenious workarounds to keep the spacecraft properly oriented towards Earth. One critical realization emerged from their efforts. A system update was necessary. In 2015, NASA put out a request for a software engineer with expert knowledge in Fortran and assembly, two programming languages that were popular during Voyager 1's initial launch. Updating the spaceship's system proved to be a daunting task, as both Voyager probes still relied on their original 50-year-old computers, equipped with only 70 kilobytes of memory. The engineers soon discovered that the thrusters responsible for maintaining Voyager's desired orientation were displaying signs of fatigue. Each time the thrusters were engaged, minuscule particles of hydrazine fuel became lodged in the pipes, gradually causing blockages within the system. Voyager had already transitioned to its backup thrusters, and if these were to fail, it would spell the end for the spacecraft. With a staggering distance of 15 billion miles from Earth, clearing the tubes posed an insurmountable challenge. Nevertheless, the small team responsible for Voyager's well-being embarked on a remarkable endeavor. They began developing a software update that would traverse the vast expanse of our universe to rectify the issue. Voyager's onboard infrastructure comprised 3 primary computers, each serving distinct functions. The main computer assumed control over all major instruments, overseeing the spacecraft's overall health and temperature, while also managing the other 2 computers. The second computer focused on Voyager's orientation, diligently seeking predetermined reference points and activating the thrusters to ensure the antenna remained pointed toward Earth. The third computer specialized in storing and handling the scientific data and images captured by Voyager's instruments. Remarkably, Voyager lacked an operating system, and any form of programming language would consume excessive space. However, this was not the first time Voyager had undergone updates. Consequently, the engineers embarked on a comprehensive overhaul of Voyager's code, executing a software update to safeguard its continued existence for the foreseeable future. However, the question lingers. How does NASA update such antiquated hardware from a distance of 15 billion miles? To grasp the magnitude of this challenge, we must delve into the inner workings of Voyager's software. For NASA to conduct a software update on Voyager, they need to install the new code into the spacecraft's computers. One of the most intriguing aspects of Voyager's computers is their memory. Each computer possesses its own plated wire memory, which stores Voyager's code in its most fundamental form, ones and zeros. This memory consists of a physical grid comprising wires and thin metal plates. Each intersection point represents a single bit of memory, capable of holding either a 1 or a 0. By passing a current through a specific wire and plate, a magnetic field is created. If the magnetic field rotates clockwise, it signifies a 0, while an anti-clockwise rotation indicates a 1. By reversing the current's direction, the magnetic field's orientation changes, flipping the bit to a 0. This process is repeated for each point, enabling the storage of ones and zeros within the memory. This design proved prudent at the time, guaranteeing the preservation of data even in the event of a power outage. Moreover, it allowed for individual bits to be updated. With a meager total memory capacity of 70 kilobytes aboard Voyager, engineers had to employ utmost efficiency in crafting their code. Alongside this fundamental machine code, Voyager has its own pseudocode, a series of shortcut commands that execute repetitive tasks without consuming excessive memory. An interpreter within the main computer reads the ones and zeros. Upon encountering a predetermined code, it triggers the pseudocode to execute a command. This approach markedly conserves memory and facilitates automated tasks without requiring extensive lines of code. However, humans cannot code solely in ones and zeros. Consequently, a more advanced programming language is necessary to write code for Voyager. Voyager's software was originally written in assembly language, augmented by a smattering of Fortran. Assembly language represents a simplistic language understandable to humans, yet closely aligned with the basic ones and zeros of machine language. Once the code is complete, it undergoes compilation into machine code, subsequently transmitted to Voyager via the Deep Space Network. Data transmission to Voyager occurs at a rate of 16 bits per second, requiring nearly a full day to complete the journey. The computers onboard Voyager operate on an interrupt-driven architecture. This means that the software follows a predefined list of instructions until interrupted. Upon receiving an update, Voyager heeds the interrupt signal, prompting the main computer to halt its ongoing tasks and enter a special mode for receiving new instructions. To update Voyager's software, NASA meticulously crafted a software update package on Earth. This package included the necessary changes and improvements to address the spacecraft's thruster and orientation issues. The update was written in assembly language and compiled into machine code, following the established programming practices for Voyager's computers. Once the update package was ready, NASA initiated a communications session with Voyager using the Deep Space Network. The Deep Space Network consists of a network of large radio antennas located around the world that enable communication with spacecraft in deep space. These antennas transmit signals to Voyager, and the spacecraft's antenna receives and decodes the signals. The software update package was transmitted bit by bit to Voyager using the Deep Space Network. Due to the vast distance, it took a considerable amount of time for the update to reach the spacecraft, approximately 16 bits per second. The signals traveled through space, overcoming immense distances to reach Voyager's location. Upon receiving the update, Voyager's main computer interrupted its ongoing tasks and entered a special mode to process and install the new instructions. The update package was carefully executed, taking into account the limited memory and resources available on the spacecraft. The new code was written into Voyager's plated wire memory, replacing or modifying the existing instructions as required. Once the update was successfully installed, Voyager resumed its normal operations, now equipped with the improved software. The updated code allowed for more efficient management of the thrusters, compensating for the accumulated blockages and extending the spacecraft's lifespan. Currently, NASA's engineers and scientists have been closely monitoring the recent weird signals to ensure the overall performance of the legendary space probe. The mission to keep Voyager 1 operational and communicating with Earth despite its aging systems stands as a testament to human ingenuity and the relentless pursuit of knowledge. Thanks for watching another episode of Beyond Discovery. While you're still here, click on the other videos you see on your screen right now.